In this video, I'm going to talk about the most advanced vectorization technique, that is nothing but Word2vec. We will understand how Word2vec will convert any text into vectors. Word2vec. So Word2vec is also a part of a word embedding. So in the previous videos, we have seen other types of word embedding. In this, we are going to discuss about Word2vec, which is again a word embedding technique, right? If we compare with a count vectorizer or a TF-IDF vectorizer, so Word2vec is a more advanced one, and at the same time, it is going to get us a precise, vector, right? So let's understand how it is going to generate the vectors and things like that, all right? So now let's see the explanation here. So say, let me, okay, give me a second. Okay. So say that I have a word, have a good day and have a great day, right? So these are two statements I have. Let's consider one hot encoder vector for each of these words, right? So we know what is one hot encoder in the machine learning. So if I try to use a one hot encoder, so how it looks like? It looks like something like this, right? Have a good day, and I have a basically good and great here. Otherwise, everything is same. For the great, I have this is the vector, right? So let's not call it as a vector as of now. We can call it as a encoder, right? So these are the encoding technique that we know. If I use this and if I want to visualize these data, so I have to think of a 5-dimensional because we have a 5 data here, right? So for where each word occupies one of the dimensions and has nothing to do with the rest, right? So no projection along the other dimensions. So what does it mean? It means that, right, good and great are as a different as a day and have, right? So it is not going to treat good and great or the same meaning. So it is going to think like different words. There's no relation between good and great, right? If somebody asks me, how are you? I sometimes say that I am good, or sometimes I say I am great. So meanings are almost equal, right? Good and great. So, but when I use this in a one hot encoding and all, it is going to treat as a different data, right? Different meanings. So what exactly I'm talking about, right? So our objective is to have words with a similar context occupy close spatial positions. So it means that if two words are giving the same meaning, right? In that case, those two words should be, in the same position, right? So it should be in the same position and it should give a same meaning. All right. So mathematically, the cosine of the angle between such vectors should be close to 1. That is angle close to 0. I will talk about this. Okay. I will talk about this end of this topic. So I will explain what exactly cosine, right? So let's begin and understand how a Word2vec works here, right? So first I'm going to import the regular expression NLTK, a string, and Word2vec, which is available in gensim.models, and stop words, right? So matplotlib, I will use it for some representation purpose. So here, what happens in the Word2vec, it is going to generate many vectors in multiple dimensions, right? So let's see that. So let me import this. And what I have done, I have taken a coronavirus related data from one of the website, right? So I just copied all the data, and so this is basically a big article, so that I have downloaded. So what I'm going to do, I am going to use this data, and I'm going to train my model on this data, right? Let's see. So as you can see, it's a very big article. I'm going to store that in one of the object called a paragraph. So now what I'm going to do here, I'm going to find any punctuations, right, and replace with the spaces. All right. So that is what I'm going to do. And after the regular expressions, numbers and special characters, day, digits, and some other regular expression related things, I'm going to replace with the spaces. All right. So one by one, I'm going to remove them. And here before that, I'm going to convert that data into a lower. So all this data, what you are seeing, so in that data, we will have a, punctuations, something like a dot, comma, right? So these things, a colon, semicolon. So I want to remove that because they don't give any meaning. And digits also I want to remove because we see some digits here. And everything I want to convert into a lower. This is an extra care to make sure that everything is converted to spaces, digits, and other things, right? And once I execute and I print this text, so this is how it will look like. Here we don't see those numbers, some special characters, right? So then next what I'm going to do, I'm going to convert that text into sentence tokenize, right? Sentence tokenization. So let me execute, right? This is how it looks like. So then I'm going to execute this sentence tokenization into word tokenization, right? So whether it is having a sentence or doesn't matter because sometimes because we have removed punctuations. So even though it doesn't matter, so I'm going to take this entire data and convert into word tokenize, right? For every sentence in sentences, right? One by one, that sentence I will use here and I will convert into words, right? So finally, I will print these words. So you can see this is how it looks like. All word, right? So we'll have all the words, one word, two word, and things like that. So then again, I'm using this punctuation here, making sure that if anything left over, I will be able to remove here, right? These are the punctuations I have, all right? So in this case, what I'm trying to do, I'm trying to, use this for loop, and let's understand this code. So a sentence word, so I'm checking the length of that and I'm using a range function so that I can iterate. Otherwise, I will not be able to iterate, right? So for every word in this, basically for every I in this range, whatever the range it comes out. So I use a sentence word, sent word, and this is the index position, right? So very first index position I will use. So now what I'm going to do, I am checking for every word in sentence word, right? Zeroed index data, the very first word. And what I'm going to do, I will check whether that word is in stop words or not, whether that word is in a punctuation or not. If it not in punctuation, then only I will store this word into that exact index location. So that way I will remove all the stop words and any punctuations still exist. All right. So that is what I am trying to do here. Now what I'm going to do, I am going to, let's execute this. Take some time, not more. Okay, so now all the meaningful words have been come out. So now what I'm going to do, everything is in this sent underscore word. So now I'm going to train the model. So that is nothing but Word2vec. So Word2vec, I am giving my entire data, right? So here I'm saying minimum count equal to 1 because one word at a time. So model is going to be trained on this particular data. Then I'm going to build a vocabulary, vocab. So this model dot word wv dot vocab. So let's print this. Let's execute and see the words here, right? So this is all basically keyed vectors and things like that. We don't understand much of this. This is basically related to location, which we are not worried about. Okay, so now what I'm going to do, I'm going to check the vectors, how it is going to generate the vectors. I will just use a COVID, right? This is the model I created, dot word2vec. I'm going to use one word and I will check the vector here. I'm going to print this vector. As you can see, for only one word, it has generated these many vectors in multiple dimensions, right? Just these, all the vectors are related to only one word, that is a COVID. If I give like a coronavirus, you see that the dimensions are changing, the vectors are changing, right? So it depends upon the word and the model on how much data you are training. So dimensions sometimes might change. All right. So this is how it is going to vectorize. All right. And if I want to check the similar words, what is the similar word for a coronavirus? So model I'm going to use word2vec dot most underscore similar. So I want to check the similar word of this guy, right? If I print that, so you see that whenever I say coronavirus, the similar words are China, cases, people, health, research. They are all related to a coronavirus. And you can see the percentage similarity. And you need to understand this similarity is based on the data which we have, and on which we have trained our model, right? If you want to generate the most similar words and all, so you have to have lots and lots of training data, right? This is all based on the data what we have fed to the model, all right? Now the similarity between infection and spread, word1 and word2. So I can say similarity, then how much it is related. It is up to 71% related. If I say that, coronavirus and let's say China, so it is 90% associated. All right. So that is how it is going to generate the data. Right. So this is basically the similarity. And which word doesn't match? So this is the word2vec model, and WV doesn't match is the method where I am giving three words here, and I want to check which one is not similar. All right. As you can see, the infection is the word that doesn't go with the spread and China, right? So China, and let me change this to COVID. So China is basically doesn't match with the COVID and spread. They are similar, right? So that's how you can interpret. All right. So fine. As you can see, the idea here is to understand how word2vec model will, vectorize the data. So it is not like a TF-IDF or a count vectorizer. As you can see, this vectorization is entirely different. And if you want to understand how it is going to vectorize the data, vectorize the word, you can refer any blog or any in a Google. So the mathematics behind it is too complex. So that's why I'm not covering that mathematical intuition in this video. But if you are interested, you can go ahead and check in the Google. So it's too huge. It's not that simple. Some of the symbols we don't even understand sometimes. All right. So I'm not getting into that part. So now coming back to the cosine similarity, right? So how initially I talked about more mathematically and the cosine similarity. So that is what we are going to understand now, right? So I'm not getting into this code, right? So I will just explain that how cosine similarity works and all. So here what I'm going to do, I have a TSNE model. It is similar to the PCA, principal component analysis, similar to that. So what I'm going to do, I'm going to check the similarities of these words, right? Similarities of these words, how close they are, right? And why do we need to understand how close they are, right? So whenever you do a Google, right? So you try to check some stories on any topic, and what happens, you will get a story and you will read it, and the next time when you log in, what happens, you will get the suggestions on the same topic, right, on the same topic which you have browsed, right? So how Google works there, so behind the scene this word2vec model is working. So that is why you see that most of the time, I would say all the time, the stories Google is going to suggest is all based on the your browsing. So if you check any cricketer name and try to browse and read a story, next time maybe some other cricketing personality story you will get on your Google homepage, right, in your mobile app. That is a suggestion. So it means that they are all belongs to one category, and that sports person, the vectors and all behind the scene are very close to each other. That is nothing but a similarity, right? So politics, you take a politics, you browse any politics related, story, and next time you will get another story related to the politic because there is a similarity. So that is what is I'm trying to explain here. So here I'm trying to check how these words are related, how close they are, right? So that is what I'm giving these words. And as I said, I'm not getting into this code. So here the idea is to show you how it looks like. All right. So now I'm going to execute this. And here you can see that, right? So now what is a cosine similarity? How to interpret this? Cosine similarity is what happens here. We assume it's a zero. So assuming, so from here it is going to check. Okay, let me take this. This is a China, right? Vector, and this is a spread. So cosine similarity is this angle. So based on this angle, so we'll be able to find how close they are. So suppose say this is a 45 degree, cosine of 45 degree, whatever the data you get. So that much close this spread and China words are. If I take a, let me delete this. Give me a second. I'll take out this. Oh, sorry. Okay. So if I take China and coronavirus, right? So the angle between this is basically cosine. So once you find this angle and try to convert that into cosine, the number what you are going to get, that is the similarity. So that is what you have seen. You have seen this guy. Well, is that? Give me a second. Right? Most similar. You see this? Most similar. Right? China, cases, people. So let's do one thing. China and cases also I'm going to plot here. Let's see. Remove this China and cases. China, I will add cases. Okay, I'm going to execute. So let's see where is cases. You see this. Okay. So if we try to plot a line here, I assume that it will come something like this. Give me a second. It's difficult. Okay, I'll take this. Okay, because they are very close to each other. So if I draw a line something like this, right? I'm sorry about that lines, right? So they are very close. They are very close. That is why you see that the percentage matching is 90% and 87, very close, right? So this is basically cosine similarity, and the Google example I gave, right? So whenever you try to check a cases, it's not exactly equal, but I'm trying to give an example. So the closest data, whatever we have close to cases, so that story you will get, right? Suppose it is a cricket, some personality here, right? So next time whenever and that personality related to sports, right? And you will get a suggestion of the same sports and different story. Maybe that data is lying somewhere here, or maybe somewhere lying here. That is very close to each other, right? So that is how you can interpret this, cosine similarity, right? Let's look into the example here. This is the famous one. So here you can see that how close these guys are, right? So mother and a boy very close to each other. Sorry about that line, right? So they are very close to each other. Similarly, fast and faster very close to each other, right? Long, longer very close to each other. All right. So that is how you can interpret this cosine similarity, and that can be done with the help of Word2vec model. All right. Yes, that's all in this video. Thank you for watching this video, and keep learning. Thank you.